Hi again. Well, we've played around with a bunch of sampling distributions, starting with different shapes of populations, and now we want to summarize our results, what we've noticed from all these, playing around with all these simulations. Okay, the first thing I've been mentioning is standard error, so I want to be more specific about what that means. So standard error, and we use SE for an abbreviation, whereas we might use SD for standard deviation. So it is a standard deviation, but it's the standard deviation specifically of a sample statistic. Okay, so the reason we use a different term is because we want to distinguish it, that it's the sample to sample variation. And we want to distinguish that from individual to individual variation. So remember with the baseball player salaries, we had quite a wide graph. And so from 500,000 up to 42 million, we had a lot of individual to individual variation. But then we saw with sample size as it got higher, the graph got narrower. So the bigger sample size you get, the smaller sample to sample variation you will get, okay? So that's why we use standard error, just to remind us that it's not individual to individual variation, it's sample to sample. But we're still calculating it in the same way. It's the standard deviation of all the sample statistics. Okay, and then the next thing I want to make more formal is what we've been talking about, what I mentioned as the central limit theorem. Okay, so here's what we saw, that regardless of the population shape, and for large enough random samples, and then from a large population, we'll talk more about that later. So there's a few conditions on this, right? And we saw that. There were some conditions. The distribution of the mean of random samples follows a normal distribution. So it's going to have that shape. And it's centered at the population mean. So we saw the mean didn't change. It stayed the same. And then the larger the sample size, the smaller the standard error. Okay, I think that makes sense that if you're averaging 100 people versus 5 people, you'd have a lot less sample-to-sample error with 100 samples of 100. Then if you have 5, you could have a lot more variation in the samples of 5, okay, because it'd be kind of spread out more all over the place. Okay, so we'll be continuing to work on this throughout the term, and then I wanted to give you a couple examples of what you might see as homework type questions or quiz questions. So state whether the quantity described is a parameter or statistic and give the correct notation. So we've seen some of these before, but we're specifically talking about means right now. So let's do this one. The average number of cigarettes smoked per person for all smokers in the United States. Okay, so is that a parameter or a statistic? Okay, average, but it says for all. Okay, so that tells me it's a parameter. And average tells me it's a mean. Okay, so this tells me it's a mean, which we're in the section of means right now, but these could be mixed up later on, so we need to know that as well. Okay, so this is a parameter. And remember for a mean what the symbol is for the mean of a population? It's mu, or like a U with a little tail at the beginning. Mu. And I'll say average number of cigarettes. How do you spell that? 1 R, 2 T's. For the population. Cigarettes smoked in the population. Okay, great. Let's do another one. Average, so we've got average again. Household income for a random sample of 5,000 households in the American Community Survey. Okay, so this one is telling us it's a sample, so that means we have a statistic. Statistic would be X bar. Average household income. So that's going to be in dollars. And I'm also going to write n equals 5,000. Because remember how our sample size changes things. So it changes our standard error. So I'm just going to write n equals 5,000. That's some more given information they gave us. Okay, great. So that's a little practice with parameter and statistic. Let's do a little more practice with central limit theorem. So example 7 here says matching sample sizes to graphs. A population histogram is shown. So here's our population. It's a large graph to the right. Is shown with a mean, mu is 10, and sigma standard deviation is 7. Okay, so we've got our population symbols here for our parameters. And we have a histogram, and it looks like it's fairly skewed to the right, yes? So it's going from 0 to roughly just under 40. Mode is about somewhere between 7, maybe 7.5. Okay, and then the question says, determine which plot A, B, or C goes with each of the following. And there's a note, it says, look at the horizontal scale as well as the shape. Okay, so we want to look at the shape, but we've also seen that sometimes the scale changes, and so we need to be aware of that. And that it's not just the shape changing, but the scale is changing as well. Okay, so we have 3 situations, letter A, B, and C, and then we have 3 plots at the bottom, capital A, capital B, and capital C. Okay, and so our options here, let me just read all 3 of them. A single random sample of 100 observations from this population. Okay, random sample, a distribution of 100 sample means from random samples with n equals 7, and a distribution of 100 sample means from random samples with size n equals 49. Okay. Okay, hold on one second. I'm going to pause this for 1 second. Okay, I'm back. This A was throwing me off for a second, but so I want to explain it well because that's why I put it on here. So A, it says a single random sample. So first I was thinking, well, there would only be one box there. But think of this as like n equals 1. So we're taking a regular random sample, so we're going to have 100 observations. So we're going to look at one sample, so we would have 100 individuals on our plot. Okay, and then we have a distribution, so then we have n equals 7 and n equals 49. Okay, so if we just took one random sample, this is like when we, in the simulations, when it showed us the original one random sample, right? And then the other 2 plots are going to be the averages of all the, or the graphs of all the random samples. Okay, so let's look at plot A, B, and C and the shape. So plot A is skewed to the right, so is plot B. Plot B is a little more skewed than plot A. A is starting to move, its center is starting to move over to the right a little bit, looking at the scale. And then plot C is very symmetric, okay? So remember how we talked about when we took one sample, the size matches very closely to the population. That's because we're taking a random sample. So this first one is going to be plot capital B. Okay, now if we take, so plot A and C are a little bit different because rather than representing one random sample, these are now averages. These are the sample means of 100 samples. Okay, so random samples of size n equals 7. Let's look at our scale. So our original population went from 0 to just under 40. Plot A is going from 4 to 18, and plot C is going from 8 to 12. Okay, so C is also narrower than A. And then C is also getting more symmetric. So I know C is going to be the larger sample size. Does that make sense from what we're seeing? So A is kind of like, B is a one sample graph. A is the intermediate, a small sample size, n equals 7. And then C is the larger sample size, n equals 49. So letter B, the second one, is actually plot capital A. And then You can see it's starting to get a little more symmetric, but not fully symmetric like plot C is letter C. Okay, so I hope that helps you. You might have some matching questions like that to match those together, and I'll see you in the next video for some more examples.